Today I intend to talk about what's known as Planck's resonators, at least for part of the time. And Planck, if you didn't know, and hopefully you kind of identified that name now because we've talked about his constant here a few times. He was in fact a scientist, very famous one because his constant is used in a variety of different fields of physics. And he was one of the founding fathers, if you will, of quantum mechanics way back in the early 1900s. And this idea of resonators emanates from what we talked about on Wednesday about black body radiation. Because remember how we said that that was a perplexing thing? No one kind of understood why black bodies work the way they do. And just for a recap, what is a black body? I might need to go over this as a real quick summary so we can understand this resonator idea very well.
It's electromagnetic radiation emitted from heated material.
Yeah. I'll draw it here too. Okay, so we have some arbitrary shape here with a small opening. So I'll draw it as such. And then the interior can have any structure. It doesn't have to be smooth. It can be rigid, jagged. It doesn't particularly matter. Looks like that. So imagine a three-dimensional shape here. And let's say we put some energy in the form of light. So there's our ray of light coming in. And as it strikes this surface, it gets bounced around a whole bunch. And different directions, different angles. Draw some arrows and show the chaos a little bit. And the point is, and the reason that it's called a black body radiator, is that the energy that eventually will find its way out, and there might be a detector out here somewhere that can gather the energy that's being emitted back through the hole, only comes from whatever is happening on the inside being energized by the incoming light that's coming in there. So every little bit isn't coming from some external source. There's nothing from the outside shell you see there that would be affecting the detector. It's only from the inside. So that's what the black body is. And we talked about some things that we can do in relation to that last time. All right, so I'll call point one here. We'll title it Planck's resonators, the US acronym. Resonators in quote, because we no longer call what's happening in here a resonator. That is a fairly accurate description of my opinion. First of all, when I say resonators, what do you think of?
Giving off.
What's that?
Giving off some sort of energy.
Like an echo, giving off energy? That's exactly right.
Good job,
Yeah, that's exactly right. Very, very good. Very nice. So we showed a graph of the energy from a black body. And remember, I put those lines, and it showed like the associated wavelength and the intensity of the light coming off. And it seemed to, as we increased the intensity, the produced wavelength got shorter, and you had a whole lot more energy in there. Well, that's not what classical physics or classical theory would have predicted it should have been. So let's show what classical theory would have told our scientists before the development of quantum mechanics. So we have our graph here. This axis will be our intensity. This one down here will be our wavelength. And there's measured in micrometers there, micrometers. Classical theory would suggest that the energy should look something like that. So as you increase the wavelength, the intensity drops, which works with what they found with black bodies. But the important aspect here of why this fails in describing atomic level things is that as we decrease the wavelength, essentially as we approach closer and closer to zero, the intensity goes to infinity. So there'd be like a limit there. And so it would go to infinity. And that's not what was observed. So let's put up what was observed just so we have a reference point here. Yeah, 1.3, that's correct. So again, we have intensity here. We have wavelength, again, my problem is there. And instead we saw a pattern that looked like that. So to compare classical and quantum right now, for large wavelengths, we see that they're pretty similar. Matches up there. Where we see this drastic change is at our short wavelength here. And we see that when our wavelength is actually 0, our intensity is 0. In other words, our energy is 0. Now logically, I think that makes more sense, and it makes sense to us now because we have a good understanding of it now. But back when classical theory was reigning by itself, this was quite bizarre. Quite a bizarre thing there. Call this point 2. We're going to get to the resonators here. So. Actually, we won't call this 2. We'll just call this 1.4. And I guess I should call this 1.1 for consistency. Does anybody have? I like to test your scientific minds. So if you saw this, what would you guess is the reason?
Something square.
I'm
Something square.
just curious. What's that?
Wait, you mean like science-wise or like math-wise?
No, you can do both. I'm
Yes.
curious.
If it's that shape, isn't it like something squared?
That's a very good observation. That's a very good observation. We will come to find that there is a squared property related to some way that you can describe the energy, say electrons in an atom. What else?
When it's its peak wavelength, peak intensity, it's a certain wave. Give you a certain reading.
Okay, so there tends to be a maximum here, right?
Yes.
A maximum wavelength associated with some energy. That's another good observation. Very good. Very good. One thing that you might notice is that this one here, tends to go to infinity here in wavelength and infinity here in intensity, which tells you that to some degree it's continuous with itself. Here we see that we actually drop down to 0 here, and that's the end of the story. So we're looking at electrons here, what they're doing. We should kind of be familiar with the atom, so I hope that was suggestive in and of itself. But what we're finding is that this experiment showed that electrons have discrete energy values. Discrete energy values. We're able to form an equation out of this. 24.1. And Planck's equation is the energy associated with some energy level within the atom as equal to NHF, where E is the energy, N is a quantum number, H is Planck's constant, and F, what do you think?
Frequency.
Frequency, very good. So we're getting our first taste here of a quantum number. You should have actually talked about this in chemistry last year, and I feel badly that you probably didn't. So I'll say it now. You're probably familiar with an atomic structure that looks something like this. Okay, so we have a nucleus with our protons and neutrons there. And then around it, we have these increasing orbits, as they were known. This is actually the Bohr model of the atom, Bohr. And what it shows you is that these levels of where we would find our electrons this would actually, well, I'd have to take some out of the middle there, but with 3 electrons it would indicate that you're talking about lithium in this example. But it's saying that this orbit here has a very distinct energy from this one down here. Now this isn't the most accurate picture of the atom today as we know it, but it still works in terms of the quantized energy states. And what we mean here is that it takes a minimum baseline energy to kick an electron up from a lower state to a higher. And likewise, when it falls back down, it releases a discrete energy amount. And that's usually in the form of light. So when we see color from something, like say my little bird up here, you see has a blue hat and a red bill or a red head and red feet and a green tail there. The light from the room is bumping up the energy of the electrons in the atoms that make him up. It's doing his little dance there. They don't stay energized. It's like a shot of caffeine or something. You know, you have to crash after a while. And when the electrons fall back down to a lower energy state, they emit light of a certain wavelength. And in particular, we're seeing red and blue and green, and our eyes are able to perceive those colors. So you might want to argue in a sense that color as we know it, or as you learned in art class, doesn't actually exist. We're only seeing the energy that's being released as an atom, or an electron in an atom, is dropping down to a lower level. So that's what this equation here is actually telling us, that, let's say for instance we know the energy, okay, and we know, say we're dealing with quantum number 1 here, so the lowest energy state there. We would be able to determine the frequency of the light that would come from that, because Planck's constant is a constant, so we know that value. Likewise, if we know this information, we can tell you the energy that's coming out of it there too. Questions? Because I know we're talking about some stuff now that you probably can't visualize very well because you can't see atoms in the familiar sense how we see everything else. And these are some very big ideas. And I will tell you that quantum mechanics is still a very growing field. So don't be surprised if there are some things that don't seem clear at first, because any physicist, any good physicist anyway, will tell you that anyone who says that they perfectly understand quantum mechanics actually probably understands it the least. No physicist has a perfect idea of what happens on the quantum scale simply because it's so bizarre. And we're going to talk about more bizarre experiments in due course, but right now we have that equation to go on. So let's make some space over here. And this would be 1.4.2. So because we have a quantum number there, we say that energy of an electron in this case is quantized. And I'll be more explicit with this right now. It's quantized because n equals 1, 2, 3. In other words, it has to be a discrete integer. So you're not going to have an n value of 1.72. It's either going to be 1, 2, 3, 4, 5, and not 0 either. So those are our n values there. each different energy represents a different quantum state. So let's assume for a minute that we have same frequency, so we'll hold that constant. H, Planck's constant, also a constant there. If we change n, put in different quantum numbers, say we start with 1 and we put in 2, we'll of course get a different energy associated with that frequency that we're producing there. And being that we're varying the quantum number, that's why we call it having a different quantum state. And the more you study physics and infinity, you go into it very deeply, you will see that quantum states actually have very interesting implications in the sense that you have a time-dependent version and a time-independent version. The time-independent version tends to be additive, different forms of quantum states that sum up to total the whole wave function itself, but that's in the future for you if you head down this path. Alrighty. I think we're good. Oh, I know, I missed a key thing. I knew I forgot something. Resonators. And it's actually a small thing at this point. We've kind of described it well enough. This idea of the electrons and stuff, Planck himself didn't know that. He imagined that there were these small things inside the black body that I did have drawn up here that were vibrating rapidly back and forth, and those are his resonators. So resonators were vibrating particles in the black body. I'll just call it BB. In the black body. So that's what he assumed was producing the energies that were coming out. You might wonder how can something that's moving back and forth generate light then? And that actually is a true thing. It's just we have a better understanding of it now. And I'll give you a perfect example. If I had a comb here or a hairbrush and I rubbed it through my own hair or someone's hair here, you know that it has static electricity on it. Okay? If you hold it next to a sheet of paper, the paper will rise up and try to meet with it. Because you've imparted some charge. There's some net charge on the comb there then. But if you pass it over a piece of paper, you notice there's a little bit of lag before the paper will rise up, like it's kind of trailing behind. That's because if we remember from when we talked about static electricity, there's an electric field that's being produced by the charge on that cone. So the electric field takes time to propagate away from the cone and interact with whatever it wants to interact with. So here's something that I think you find quite bizarre. At least I did the first time I heard it. Let's say then we take that cone and we start waving it back and forth. If you imagine the electric field as being a line, it's actually many lines coming down from it if you want to be more specific. But as a line, for the sake of this example, like a rope that you wiggle back and forth, you'll give it a wave tendency as it goes down to meet whatever it's meeting with. If I do that fast enough, the waves that I'll produce there will eventually fall into the infrared range, or it'll start to reach parts of the electromagnetic spectrum, so you'll actually get some heat produced by that. If I wave it a little bit faster, you'll eventually start to see visible light that comes from that, because the wavelength will then match colors that we can see, so we'll go through the rainbow, going up to blue, because that's the highest. If I go faster still, I'll start to produce ultraviolet waves, and if I go faster, I'll eventually start to produce gamma radiation out of that. It's kind of interesting to think that you can produce that thing from putting a charge on a comb and waving it back and forth in theory. And in fact, there have been labs around the world, and this is actually an older thing now, they probably did this 70 or so years ago, or longer, that have produced light that we don't actually have in the electromagnetic spectrum, so they imparted such a small wavelength to it that actually exceeds that of gamma radiation. We technically don't have a physical name for that. So interesting thing there. All right, I have a practice problem that we can do, and it's rather long. So bear with me for a minute while this loads up. And
Do you want this recorded?
yeah. There we go. Okay. I've posted this on Edmodo, so you can find it there. We're just going to work it out in class here. That way I wouldn't have to take 20 minutes writing it on the board. So a 2-kilogram mass, and I guess I should read the title first, a quantized macroscopic oscillator. So we're talking about big things here. We're not talking about little atoms. We're going to see if we can apply the same principles of atoms to big things and maybe draw some conclusions from that. So a 2-kilogram mass is attached to a spring having force constant K equals 25 newtons per meter and negligible mass. So the spring is stretched 24 meters from its equilibrium position and released. Hopefully, if you remember from, we talked about oscillators, harmonic oscillators. We had like that K value when we were determining our force, negative K times our displacement gave us our spring force there. Okay, so released from its equilibrium position. So A, we're going to find the total energy and frequency of oscillation according to classical calculations. B, assume the Planck's law of energy quantization applies to any oscillator, atomic or large scale, and find the quantum number n for this system. And again, if you're really writing this down, maybe just hit bullet points or something, because you can find it online. I've shared this on there. And lastly, C, how much energy would be carried away in one quantum change. In other words, if we drop down an energy level, how much energy would be associated with that. All right, so part A. Part A, okay, so if we're looking at the energy from a spring here, and this will actually be a new equation for you, because I don't believe we went over this with springs. We talked about the force but not the energy, but it should take a familiar form for you. So it'll be E equals 1/2 Ka squared. A here is our amplitude, which we know our amplitude is 0.4 meters. That's its displacement from equilibrium, 0.4 meters. Why does this look familiar to you, hopefully? We have them.
What's that?
Should look like another kind of energy.
Is it like potential or kinetic?
Kinetic. It looks like the form of kinetic energy, which is 1/2 mv squared. And so here, this is the form of it that works for a spring. All right, so just plugging in our values, then we'll have 1/2 K. We said it was 25. Our amplitude there is 0.4, so 0.400. We'll square that. And we produced something along the lines of 2.00 joules. Joules are energy. And now frequency. Frequency of a spring or an oscillating thing. This should also be new to you, but it's not. 1/2 pi times the square root of K there, so we have our constant over M. So it's our mass. Plugging in these values, 1/2 pi. K we said is 25 again, divided by mass was 2 kilograms. It's something along 0.586 hertz, if I'm not mistaken. 563. 563. I was close.
Where did that equation just come from?
This is just a new rule. New frequency of a oscillating thing or a spring. I wouldn't expect you to do them this quickly, but I've done these before, and I know the answers beforehand. Which is a good advantage. So this is part A. So look here, we found our energy. and we found our frequency. Hertz is how we measure frequency. So B wanted us to assume that Planck's law of energy quantization, so that's that E sub n equals NHF applies to any scale. So we're finding n here. So En equals NHF. Rearranging to solve for solve for n, I'm sorry, we'll have n equals En over HF. Well, we know our energy now. We did that in part A. It's 2 joules. Planck's constant is 6. What's Planck's constant?
6.66 times 10 to the negative 34th.
I'm just going to use 6 to all around here. 10 to the negative 34th, which was seconds. Our frequency, which we found over there as well, 0.5863. I don't know why I keep wanting to say 8 and half-this. And our quantum number that we'll get there if we work it out is 5.36 times 10 to the 33rd. No units, because remember n is just a number. We'll talk about that explicitly here in a moment.
This is constant.
Alright. So now we have part B, there's n. C wants us to say how much energy would be carried away. Okay, so we're looking for the change in energy here. So delta E equals E of n plus 1, because we have one higher energy, minus e to the n equals, work this out for you here. This would be n plus 1 would be 2 HF minus 1 HF, or just HF, giving us just HF. Plug in our new values here. Planck's constant 6.63.
Is there more?
Yeah,
How did you get that equation?
this one?
Yes.
Well, this is not a standard equation by any means. It's asking for the change in energy from one quantum change. So we have e to the n. So let's take a condition where we are one higher, n plus 1. So our e to the n originally could have been 3, in which case this would have been 4 then. So we're just taking one higher and looking at the energy difference between the two. Alright, our frequency again is 0.56 hertz.
And the 2HF is same thing as energy but in different words.
Yes, it comes. So n plus 1, this is just 1 for n here, 1 more would be 2. So whatever number you have here is a number that goes in for n. And we would get 3.73 times 10 to the negative 34 joules. And there we go, we have our change in energy. Alright, so let's look at the change in energy here. This is an incredibly small number, times 10 to the negative 34. This would be unmeasurable. We don't have any sort of equipment or sophisticated machines that can measure energy changes that small. So even though we can look at the quantum nature of macroscopic things, the results that we get are so tiny that it just doesn't make sense that we would apply these rather than classical principles to classically large systems here. Now, when we get down to the atomic scale, these numbers become much more measurable. They don't become these absurdly small values here. Questions? All right, if there are no questions, then we'll take our break and we'll do photoelectric when we come back.